Welcome to the last part of our lecture in this series, and here we would wrap up the discussion on logic gates and their what is a physical electronic point of view implementation, which are through the transistors. So we would finish this up with a with an understanding or with an introduction to this logic IC chips, something which is called the logic IC chips. So if you had a lab session, actually, then you would be introduced to them directly. You would be able to see them, touch them and work with them. Probably in the next semester you will be doing this. Let me just introduce you to the logic IC chips. So IC means integrated circuit, and what does this mean is basically a lot of transistors are integrated together in a circuit within this space, within the space inside this black covering or black casing. You can see some pins are coming out. On the other side also there are pins coming out. So these pins are the access to the gates which are constructed within this chip by some arrangement of the transistors. So we will look into, in this lecture we will introduce ourselves to something called the data sheet of a logic IC chip, and the data sheet reveals a lot of information about this particular IC chip, how to use it, and some different physical parameters of that chip. So we will introduce ourselves to some of those, and that would form some basic knowledge which we require to go ahead with working with this sort of logic IC chips. Now this is the 7400 chip. So here you see 74LS1N191N. this is a different number. So what we are actually looking the data sheet is for 7400 IC chip. So 7400 IC chip is the IC chip for the NAND gate. That means all the gates within it are the NAND gates. You see, this is the gates inside this chip. So 7400 will also look very similar to this. So so here you inside that chip, the circuit that has been made will have NAND gates in this fashion. By using the phrase in this fashion, what I mean is that the inputs of this AND gate are from the terminals 1 and 2, and the output is coming out from terminal 3. So you have to understand that in this particular 74, suppose this is 7400, I did not get a very nice picture of 7400, so I took this. Suppose this is 7400, then this is your pin number 1, this is pin number 2, this is pin number 3. So pin number 1 and pin number 2 are the inputs to this NAND gate, and pin number 3 is the output to this NAND gate. Now you are having a very physical thing with you, and if you want to do NAND operation of two logical variables 0 and 1, you would supply those variables in these two input pins, and the result of the operation you can extract from this output pin. You will see whether it is 0 or 1. So in that mode you can perform some experiment to see whether the NAND operation is being performed by this NAND gate within this chip. So it will be performed, and it is a verification. So this is one of the experiments that you will do actually. Similarly, you see that there is another NAND gate with the input terminals 4 and 5 and the output terminal the 6, and the 7 terminal 7 is the ground. So you see here are 8 terminals. So this is for this 7 LS191, and there may be 8 terminals in this side. So in 7400 there would be only 7 terminals in one side and 7 terminals on the other side. So the terminal number 7 is the ground terminal, so for 7400. So the next terminal that comes just opposite to 7 is 8, and then 9, 10, 11, 12, 13, 14, and 14 is the VCC terminal. So that means you have to supply your supply voltage, which is plus 5 volt, to VCC and ground to 7. Unless you do that, the entire IC chip will not be working. So if you connect some variable in 1 and 2 and expect an output from 3, you will not get the correct output, or may not get any output, unless you have connected the VCC and ground to this IC chip. So that is very important. So that's why we need to know where the VCC and the ground pins are in an IC chip. We have to connect them first, and then we have to work with the gates. Now suppose you need to connect two you need to use NAND gates in a particular digital circuit, then you can connect this NAND gate. So in that particular circuit, if you need to connect 2 terminals to a NAND gate input, you take those 2 terminals and connect to pin 1 and 2, and take the output from the NAND gate and again connect it back to some place of the circuit where you need the output to go. So in that way you can form circuits using these IC chips on something called a breadboard. So you will do all these things when you are doing the actual experiment. In this particular lecture, I will simply introduce you to the IC chip and some of its physical parameters that we need to be certain about. So this is a data sheet which provides you with all these physical parameters. So first thing in the data sheet that one must notice is the arrangement of the gates within the IC chip. That means the input terminals and the output terminals of the gates, how many gates are there in the chip, and the VCC and ground terminals. Also you see there is a truth table given of this, or this is called the function table, which is the same as a truth table. It is written in low high sort of a convention, not with 0 and 1s. Now the physical things that we need to be concerned about are these operating conditions. So supply voltage, what would be its supply voltage? Minimum, maximum, and minimal, nominal, maximum, what is the units? So these things you can look up from here. So for this particular 7400 to work, you will not give a supply voltage of 3.3 volt, you will give a supply voltage of 5 volt. That would make it work. So VCC, what is the nominal value that has been given to you? So you would give that value. You would not give 9 volt. So what exactly supply voltage you need to give, that is mentioned in the VCC. Similarly, other various parameters are given, and you can also see you have this low level input voltage. So if that is maximum is given for the low level input voltage. So 0 to 0.8 is considered as the low voltage, and what is the high level input voltage? That is from 2, the minimum has been given. From 2 to 5, it is the high level input voltage. Similarly, you have some current ratings, and there is some temperature rating, working temperature sort of thing, and then you have this, all the different electrical characteristics are given here. Not everything is needed for us, but these are some information regarding the gate. And if you want to study a gate or do some higher level study, or go into designing of these sort of IC chips, you need to know which are the different characteristics you should be concerned about. So all these things are given here. This is something important which we need to know. There is something called the propagation delay time. This is a switching characteristic. So the logic gates inside this IC chip will take some time to switch from low to high and high to low. There would be some time taken to change its state from low to high and high to low. So when you are actually changing from low to high, suppose this is the low level and this is the high level, it would not change instantaneously. So like this, it would not happen like this. There would always be some definite time taken for this change to happen. So this time is called the propagation delay time. And as from 0 to 1, some sort of time would be taken to come from 1 to 0 also. So it is the low to high propagation delay time, this is the high to low propagation delay time, and both can be different. As you can see here, both can be different. So it says maximum, because maximum we would spend 22 units of time to go from low to high. It will not exceed. So that guarantee the manufacturer is giving us. Similarly, high to low, maximum it can be 15. It will not be more than 15. That guarantee is with us. Now what is that unit? Unit you see is very small actually. It is in nanosecond. So practically it may be very insignificant. However, for very precise applications, and when we have a very fast baud rate, so the bit rate is very fast, and suppose you are transmitting bits which are below 22 nanoseconds or below 15 nanoseconds, you have to change your state from 0 to 1 or 1 to 0, then there would be a problem, because it needs at least this much of time to come to the stable state of 0 or 1. Only after this you can actually perform another change of state. And also, if you sample within 15 seconds, within 15 nanoseconds, you might not get the correct result. So your sampling frequency, after you have changed a state from 0 to 1, you must check that change state after 15 nanoseconds, after 22 nanoseconds in this case. Then you are guaranteed to get the state as 1. So even after 22 nanoseconds, if you are not getting the output as 1, then there is some problem, perhaps in the circuit or somewhere else. You can recheck, re-verify that. But if you are trying to sample before the propagation delay time is over, then you might not be, you will definitely or you might not be getting the correct result. Okay, that is the significance of propagation delay time. So here are some pictures of the different things on the physical side, some mechanical dimensional things. And one thing I forgot to tell you, how to know which is the pin number 1 by looking at the physical chip. So you see that there is always a groove like this in the chip. So the left side of this groove, so if you look at the groove directly, then this is the left side of the groove. The pin to the left side of the groove is the pin number 1. That is by convention. So this is why the groove has been placed, to help the user identify the pin number 1. And from here the counting starts like this and then goes in this order. It is not like this and then again like this. It does a complete round. So here 1 2 3 4 5 6 7 8 9 is here, then 10 11 12 13 14 15 16. So it is not that 8 is here and then 9 is again from here. It is not like that. 9 is here. Okay, so these are some of the things which needed to be told, and some few more things are there. These 3 things which are not, which in this data sheet it is not shown, but one needs to know that there is something called the noise margin, fan in and fan out in context or in relation to a gate, any gate. So this is a NAND gate. It is true for all gates. So this propagation delay time is also they are present for all different gates. So different gates will have different propagation delay time, different noise margin, different fan in and different fan out, and this will also vary across manufacturers. So this particular manufacturer, which is this Fairchild. So Fairchild has manufactured this NAND gate IC chip, and their propagation delay time we noted 22 and 15. If some other manufacturer may supply with lesser propagation delay time, it can so happen. So one has to know all this by reading the data sheet and choose wisely on which manufacturer to go with. So all these things are there. Now what is the noise margin? Noise margin, as you can already have read perhaps, it is the maximum external noise that can be added at the input of the logic gate without changing its output. So this is almost like that change in the level. There was this dead zone, right, where we are neither 0 nor 1. So in that dead zone, so how much actually we can actually have a external noise in the input so that we don't go into the dead zone. That is what it is trying to say. So suppose 0 is the low level, and if we cross 0.8, then we are in the dead zone. So we don't know whether we are 0 or 1, whether we are high or low. So then 0.8 is the noise. So this is the noise margin for the low level. Similarly, in the high level, if you are high from 2 to 5, then at the high level 5 you can come down till 2. So the noise level is 3 volts in this case. So after crossing 3 volt, you will come to the state where your output might change. Okay, so that is the significance of this external noise, which is basically the input, the high and the low voltage ranges. By looking at that, you can understand what would be the noise margin. Fan in and fan out. So the number of input pins available to a logic gate is the fan in. So I showed already that you can have gates where you have multiple inputs, not just 2 but maybe more than that. You can have gates like this. So this is a 4 input AND gate, this is a 3 input NAND gate. The fan in is the number of input pins available to a logic gate. So that is the fan in. What is fan out? The number of logic gates that can be driven by the output of the logic gate. So like this output, you might want to connect to some gate here. So since I don't know what that gate is, I am drawing a square block. Okay, it may be some gate, I don't know, some gate G1. You can wish to connect it to this same output, you can wish to connect it to some other gate, and likewise you can wish to connect the same output to so many number of gates. So how many number of gates you would be able to connect the output of this particular gate is the fan out of this particular gate. So that is what is the fan out. So it basically is the current strength that one can deliver at the output of the, it depends on the current strength that this gate can deliver. So the maximum current that can be delivered by this particular gate, that determines the fan out basically. So this was all that I needed to highlight, and with this we come to an end of our understanding of logic gates and the electronic circuits which build these logic gates. From the next lecture onwards, which will start a new module, we will actually work with these logic gates as the basic building blocks. We will stop looking into the electronic circuits which make up these logic gates. We will start looking at the logic gates as the basic building blocks. So we will have 2 inputs or 3 inputs coming to our logic gate and the output coming out of that logic gate. We would like to know what different set of inputs will produce what output in terms of zeros and ones. So that is the sort of thing we would start working with, and hence it is very important to know the symbology of the logic gates, the symbols of the logic gates and the truth tables of the logic gates. All the logic gates that we have studied, AND, OR, NOT, NAND, NOR, XOR, XNOR. So these 7 logic gates, one has to be thorough in the use of symbols as well as in the knowledge of the truth tables of these logic gates. Only then one would be able to go ahead and use these logic gates to build some complicated circuits, okay, digital circuits. That is where we will begin from the next lecture. Okay, so this is all. So thank you for paying attention and see you in the next lecture.